Now we consider pseudo tensors and then dual tensors. For that we consider the coordinate transformations where we have the reflections or inversions. Okay, we have been considering rotations as the coordinate transformation. The rotations are not the only kind of transformation, coordinate transformation that we see. We see reflections, inversions as well. Okay, and in the case of reflections, or in the case of inversions, we see how the coordinates are changing. First of all, let's take inversion. Here we have three coordinates: x1, x2, x3, and this is a vector in this space, vector r, right? And we have the coordinate transformation, x1 prime, that is, the inverse or the inverted one. This is x1, and x1 prime is in the opposite direction. And we had the x2, this is x2, so x2 in the x2 prime in the opposite direction, x3 prime. Okay, so these are the inversions, x1 prime, x2 prime, and x3 prime. And in this coordinate system, the new vector is r prime. New vector is the r prime. Okay, this is the original coordinate system, and this is the inverted coordinate system. But here the coordinates now become the r prime now becomes if vector r as the coordinates x1, x2, x3, vector r prime has coordinates x1 prime, x2 prime, x3 prime. And since what we have done is inversion, what happens is x1 prime now becomes equal to minus x1, equal to minus x2. x3 prime now equal to minus x3. Okay, and we have this transformation x1 prime, x2 prime, x3 prime equal to this minus 1 0 0 0 minus 1 0 0 0 minus 1 matrix x1 x2 x3. This matrix multiplication will clearly give you minus x1 minus x2 and minus x3. Okay, so this is what happens in the inversion. Our vector is the original one is this, transforms into r prime, which is minus x1 minus x2 minus x3. The position vector and all other vectors whose components behave this way or behaving this way, that is reversing sign with the reverse of the coordinate axis, they are called polar vectors. These are called polar vectors and have odd, they are said to have odd parity. So if you reverse the coordinate system, what happens? The reversing of the sign occurs, because x1 prime is now minus x1, x2 prime is now minus x2. Okay, so such vectors, such quantities are called polar vectors, and they have got Wood parity. We say they have got Wood parity. So vector A prime in the transformed or inverted coordinate system, the components are A1 prime, A2 prime, A3 prime, and it is minus A1, minus A2, minus A3, and it is a polar vector. Okay. Now consider a vector defined as the cross product of the polar vectors, C equal to A cross B. So we have two polar vectors, A, B, and we are taking their cross product. And we know how to take cross product. What we have to do, we have to take I, J, K, here A1, A2, A3, B1, B2, B3. So I, A2, B3, A3, B2. That will be the first component. So C1 will be A2, B3 minus A3, B2. Okay. So when coordinate axes are now inverted, A2 prime, you know, that becomes minus A2, A3 prime becomes minus A3, B2 prime becomes minus B2, B3 prime becomes minus B3. Okay. So A2 prime becomes minus A2. A3, since these are all polar vectors. So what happens is, as we take the C1 prime in the new coordinate system, we know C prime, that is A prime cross B prime. So C1 prime will be A2 prime B3 prime minus B2 prime A3 prime. So this is C1 prime, and that is equal to, if we substitute for A2 prime, which is minus A2, so for B3 prime we substitute, which is minus B3, for B2 prime we substitute, which is minus B2, for A3 prime we substitute, which is minus A3. So what we are getting is A2, B3 minus B2, A3. Okay. So this is what we get, and Ci prime, which is which is same as C1. So generally we can write Ci prime is equal to Ci. So our cross product vector C does not behave like a polar vector. If it is behaving like a polar vector, Ci prime should have been equal to minus Ci. What we are getting, Ci prime as equal to Ci. Okay, so this is not behaving like a polar vector under inversion. To distinguish, we label it as pseudo vector or axial vector, and we say it has got even parity. Okay, we say it has got even parity. The term axial vector is frequently used because the cross products arise from a description of rotation. So velocity is omega cross r, v equal to omega cross r. Okay, the cross products related with rotation, angular momentum, r cross p, torque. Okay, and dou b by dou t minus del cross e. Here omega is an axial vector or pseudo vector. Angular momentum is an axial vector. Torque is an axial vector. Okay. Magnetic field is an axial vector. So it's related with the rotation. So with respect to inversion, we can have polar vectors and axial vectors or pseudo vectors. Okay. Now the distinction between polar and axial vectors may also be represented by a reflection. Okay. The distinction between polar and axial vectors may also be represented by a reflection. See here we have x, y, z. So this is we suppose that we have a mirror in the xz plane, and this vector, as it gets reflected, you will have p prime. Okay, it undergoes reflection in the xz plane along the y-axis, or we can say along the y-axis it gets reflected. Now what happens is, as it gets reflected, there will be no change in xz components. Okay, there will be no change in xz components, and the new vector p prime, there will be no change. Px prime will be equal to px, pz prime will be equal to pz. But what about py prime? That will be equal to minus py, because it's getting reflected. See the vector that as it gets reflected, it's pointing in the negative y direction, its component. There will be no change in the components along x and z direction. So our p prime, vector p prime, px prime, py, pz prime, that will be px minus py, pz. Now an axial vector, such as a magnetic dipole moment. Okay, magnetic dipole moment, that is current into area of the current loop, that behaves quite differently under reflection. Okay, an axial vector such as a magnetic dipole moment, that behaves quite differently under reflection. See here we have the current loop, and this is the magnetic dipole moment corresponding to this. The current is flowing in this, and the current is I, and the area is A. So IA is the dipole moment. Current is flowing like this, and its components are mu x, mu y, and mu z. Now what happens is, as it undergoes a mirror reflection or along the y-axis, a mirror in the xz plane, the current flowing here, it will be flowing like this. So the current will be flowing like this. Okay. Now as the current is flowing like this, the magnetic dipole moment will be in this direction. Okay, the net effect is, if you take mu prime will be mu x prime, mu y prime, mu z prime, that we know, but this will be minus mu x, this will be minus mu z, and this will be mu y. So mu y prime is equal to mu y. Okay. So mu prime is equal to minus mu x, mu y, and minus mu z. Similar restrictions apply to scalars and pseudo scalars. Okay. And in general to tensors and pseudo tensors. Okay, so same thing, in the case of a vector, we saw it as polar vector and pseudo vector, and this is quite general. It applies to tensors. Okay, so we have pseudo scalars, pseudo vectors, pseudo tensors, and they transform like this. Pseudo tensor will be transforming like this. S prime is modulus of S, modulus of A into S. This is a scalar. This scalar transforms like this, a vector. Ci prime is magnitude of Aij Cj. Okay, and in the case of a tensor of rank 2, its transformation is like this: Aikjl, Akl. And this is the determinant, which is the matrix corresponding to the transformation. If it is kind of a reflection along y-axis, this will be the matrix, and the determinant corresponding to that is determinant A. And if it is kind of inversion, if it is inversion, the matrix will be this. This will be the matrix. Okay. So the pseudo scalars, pseudo vectors, pseudo tensors transform according to this relation. Okay. So this is all about the pseudo tensors. The interesting thing is the determinant A, array of the coefficients A, M, N, its its value is -1, and for reflection on x-axis, if we are taking reflection on x-axis, previously we had taken reflection along y-axis, so we had -1 here. Okay, but if we are taking reflection along x-axis, we have -1 here. For reflection inversion, if you take the determinant, its value will be equal to -1. But for rotation, the determinant is always equal to +1. Okay, for rotations, it is always equal to +1. So anyway, this determinant will be equal to -1, and pseudo tensors transform like this.